minimal surfaces, the area volume of the limit is only less than or equal to the limit of the volumes, or the limit of the volumes, right? And so you have to argue that you don't actually have area concentration near the boundary, and so that uses the free boundary condition and a monotonicity kind of argument. So for free boundary surfaces, there's a monotonicity argument near at the boundary, an approximate monotonicity, which can be used to show that in fact the areas converge. So in particular, you get that the limit of the areas is 2 pi, and so in particular the sigma 1 times L, sigma 1 is 1, the lengths can actually converge to 4 pi. So that's the result. Yeah, so so in particular we have so it's a sharp upper bound asymptotically for genus 0 k. Actually, it would be nice in the compact surface case to prove such a theorem as the genus goes to infinity.
That's what they call it, right?
What's that?
That's what they call it. They call it. They call it about high T.
Not sharp. No, you can only prove.
Well, that's not.
You can only prove course.
That's already been a treatment just to prove it.
Well, no, this is it'd be interesting to understand the limit of the maximizers. Okay, and so the Mobius band is actually a similar analysis of the critical platinoid. So actually it's a little nicer formula for sigma 1 times L there. And so again, the statement is that this maximizes the metrics of the Mobius band. And again, the proof is similar. So we prove the existence of the maximizing metric, and then this gives an immersion into Dn by first eigenfunctions, and then use the uniqueness result to show that it's covered. So I have about a half an hour left. I can let me. So I might not have time to prove both of these things, but so I can either do the proof of the uniqueness theorem for the critical platinoid, or give a sketch of the existence of maximizers. Does anybody have any preference? So the uniqueness for the critical platinoid is more of a sort of geometric complex analytic argument. The other one is more of a hard analysis type argument. Are more people hard analysts or geometry? Let me talk about this one because I think you'll be able to understand all the steps in this, whereas the other one requires quite a lot of thinking to make do the check there. So this one has a very clear idea. So again, I'm going to show that if I have a free boundary minimal annulus at Bn such that the coordinate functions are the first eigenfunctions, then in fact n is 3 and I have a critical boundary. Okay, so in fact I can get off easy with the n equals 3 result because I can just quote the multiplicity bound, which tells us that. Now actually, you could do this without using the multiplicity bound. That is, you could a priori assume you're at Bn for any n, and then you could argue at the end that you're actually in B3. In fact, that's how we do the critical Mobius band. Let me say that after we posted our paper, it was shown by several authors, Hunter really is one of them, that in fact for arbitrary metrics on the Mobius band, the maximum multiplicity is 4. So they proved a multiplicity bound. If you look at the usual multiplicity bound, it gives you something like 7, much worse than 4. But they improved it and were able to prove the multiplicity is at most 4 for the Mobius band. So in particular, the critical Mobius band has the maximum multiplicity, which is sort of what you would expect. I guess the maximizing metric should have as high multiplicity as possible. But that wasn't known at the time we wrote the paper, so in the Mobius band case, we allowed the possibility that we were in a higher dimensional ball. Okay, so and so the way we do this is, first of all, we understand the conformal structures on an annulus. Namely, the annulus is equivalent to, conformally equivalent to just the product of the integral of the circle. Coordinates t and theta. And then the idea of the proof is to show that to show that the vector field dd theta, which is a conformal killing vector field, it generates a one parameter group of conformal transformations, to show that it's actually generates isometry. So the key is to show that the vector field x, which is the push forward of dd theta, so dd theta, is to show that that actually is a rotation vector in R3. And the key step for doing that is to show that the three components of x, so x is just a vector field in R3, so it's components x1, x2, x3. The key step is to show that the three components are first eigenfunctions. So if they're first eigenfunctions, then they're linear functions. Once they're linear functions, it's not very hard to see that the vector fields are actually rotation. So the rotation fields are like, x1 minus x2 minus x1, so x2 dx, 1 dx2. So the coefficients are linear. They're functions of coordinates. Okay, and so what we do is we look at a quadratic form on vector fields, which plays an important role. So we call it Q. And so if we think of vector fields y, defined along the surface, so these are vector fields in R3, they're not tangent to the surface necessarily, but they do have the property that they're tangent to the skew along the boundary. So I look at vector fields y, so y is tangent, it's tangent along the boundary, so y is tangent to the skew along the boundary, but inside it may be neither tangent nor normal. So we look at such vector fields, then we consider the quadratic form. So we just think of the components, y1, y2, y3, as functions, and then we take the Dirichlet, the sum of the Dirichlet integrals. That's this first term, integral over sigma, y squared, and then there's a boundary term, which is the integral over the boundary, the norm of y squared. That quadratic form has an interpretation as a second variation of the energy itself. And so the observation, the connection with the eigenvalue problem, is that this form is always non-negative definite if I know that the integral of y in the boundary is 0. And that's just the eigenvalue condition. This is the Dirichlet integral, and this is the integral of y squared. So if I knew that y integrated to 0 around the boundary, then I would get q as non-negative definite. So it's non-negative definite for such vector fields. And in fact, equality holds here if and only if the y's are first eigenfunctions. Okay, and so then the idea is to look at this form applied to the rotation vector field x. Okay, and so it's not actually very hard to see that x is in the null space of this form. So if you take q of xy, or y of this type, you get 0 for any y. So it's in fact in the null space. X is in the null space. So in particular, of course, qxx is 0, so it looks like we're done. But the problem is, of course, it doesn't satisfy the normalization. The fact that the integral is 0. Okay, and so that's the key point we have to understand. And so so I make the observation that q is the second variation of half of the energy, where the energy for the map, so I have a map d into d3. I consider variations of d defined by y, and I compute the second derivative of 1/2 the energy of the map, and then I get that form, where the boundary term comes from the fact that I'm allowed to move the vector field, I move the surface along the boundary, not fixed along the boundary. So it's that the second variation. Okay, and so the idea now then is to find a vector field y which has the property that q of y is less than or equal to 0, so it's negative for the second variation, and so that when I subtract y from x, I can achieve the integral condition. So if I could do that, then I would have something good, because then q of x minus y is less than or equal to 0. That's because x is in the null space, so this is equal to q of xx, which is 0, and then minus plus q of y, which is plus 0. Okay, so that's what I need to do. In other words, I need to take this x and I need to shift it using a special kind of special choice of vector field. Okay, and so And so actually, once you get the x minus y first eigenfunctions, then if you understand what y looks like, you can finish it through. Okay, and so really the key is to find these vector fields y. Okay, and so actually, initially we thought that the vector fields y should be conformal vector fields in the ball. Okay, so there's a natural family of vector fields in the ball for which you can achieve the normalization, which are just the conformal vector fields in the ball. However, we were never able to show that the conformal vector fields actually reduce the area. So this has an analog for surfaces, for minimal surfaces of the sphere. So if you do it in the sphere, then the conformal vector fields always reduce area of the second order. That appears not to be true for free vector manifolds. So we had to work a lot harder to do this. And the idea is to replace the second variation of energy by the second variation of area. Okay, and so I've written that here. So if we consider the second variation of area for normal vector fields perpendicular to the surface, then that turns out to be this expression. So this is this. So the variation is psi times the normal. So that x is psi times the normal. Then when I compute the second variation of area, so that's not a conformal definition, but I consider second variation of area, then I get this expression. So this is the usual second variation of quadratic form, the index form, and this boundary term again arises because I'm allowing psi to be non-zero on the boundary. So when I move the boundary, it tends to reduce the area. So I get that. Okay, so A here is just this sum of squares in terms of curvatures. Okay, so these are for normal variations. And so, right, so these variations, because of the free boundary condition, these automatically are tangent to the boundary sphere. Okay, and so the key is to understand the relationship between Q and S, quadratic forms Q and S. So notice Q has a natural null vector, namely the rotation field. S also has a natural null vector, which is the dilation vector field, x dot nu. So it's the normal component of x, which is, so x generates dilations. And so if you take the normal component, that's the corresponding. So that's a Jacobi field on the surface and 0 along the boundary on the free boundary condition. Okay, so that's in the null space of this S. Okay, and so it turns out that for S, for the second variation of area, there is actually a natural n-dimensional space, or in this case, 3-dimensional space of variations which reduce the area. And so what these are just given by parallel vector fields in R3. And so if you take a parallel vector field in R3 and you take its normal component, so we have our surface, you take some parallel vector field V, and then you take its normal component. This would be V dot V times V is our variation. So notice that the normal component of V is tangential to the sphere. So on the sphere, these vector fields actually are conformal vector fields. So if you take these vector fields and take their tangential projection to the sphere, those generate families of conformal transformations, the dilations. However, they're not conformal inside. So these don't. They're just these translation vector fields. So it turns out that for the sphere, there's a very special thing happens for the boundaries of the sphere, and that is that for this three-parameter family of variations, they're all negative with the exception of variation. In fact, this is actually strictly negative unless the infinite terminate. Okay, so that's one part of the argument. There's a three-dimensional space of negative variations for the second variation of area. And in fact, if I include the dilation vector field x dot nu, I get a four-dimensional space for which S is non-positive. I have a four-dimensional space. And now the problem we looked at is the question of relating the second variation energy to the second variation area. Okay, so we can ask the question, suppose we take a normal vector field, psi times nu, can we add a tangential part to it so that infinitesimally the deformation preserves the conformal structure. Okay, and so that's, and it turns out that that it's just an equation, for doing that, it's just the equation that, take the corresponding vector field y, it's just the equation that del, we take it on a normal basis, del pi y, del pi y, the equation, sorry. Some of those, it's a sort of conformal filling equation. So this is minus that, and del d1 y dot d1. Okay, so here y is not tangential. Y is, so if y were a tangential vector field, these are the conformal filling equations. They say that y is a holomorphic vector field or a conformal vector field. But y is not tangential, it has a normal component. But what we could try to do, but this is the condition that says that when we deform the surface in space, the conformal structure doesn't change in the first order. In particular, it's the condition which says for these y's, the quadratic form q is equal to the quadratic form s. Okay, so that's what we need to do. So what we need to study is the problem of whether we can take a normal variation, add a tangential part to make it preserve the conformal structure. And it turns out if you write that down, it involves, it's a Cauchy-Riemann equation with a boundary condition, because you want y to be tangential at the boundary. So you need the vector field y to be tangential to the sphere, so the tangential part has to be tangential to the surface along the boundary. Okay, and so that's a Cauchy-Riemann equation for the boundary, and so we can analyze it. Okay, and it turns out the problem actually has a one-dimensional co-kernel. So there's an obstruction to solving it. It's generally not, so the operator is not surjective, but there's a one-dimensional orthogonal complement for the image. And so there's a one-dimensional obstruction to solving it. And so in particular, in order to meet that obstruction, so we have to check that we can act, the dimension count is actually rigorous, but what we need then is if we want to construct a y so that the integral of x minus y0, that's three conditions. Right? We need to meet three conditions. And so we need to do that with a conformal vector field. Okay, and so in order to meet those three conditions, we need a four-dimensional space of conformal vector fields. Okay, and so the four-dimensional space is exactly this one. It's spanned by the translations to 3 and then x dot 2. So those are actually independent, and then you can argue that in fact you have exactly enough freedom to achieve that, and so you can argue that you can construct such a y so that the integral of x minus y is 0, and then you can complete the so once you make the integral of x minus y 0 and q less than or equal to 0, then x minus y's become eigenfunctions, but then we know sort of what y is. At least we know it's a linear combination of these guys, and then we can analyze this equation. So that's the idea. So it's a rather, I think, a rather interesting second variation argument involving the second variation of the eigenvalue condition. So actually, there are several works in the literature where people try to understand the connection between the second variation of energy and the second variation of area, and this is kind of in that spirit. Okay, let's see. So I have about 10 minutes left, so maybe I can just say a little bit about the existence part. Let me just say. Let me first sort of look at kind of an obvious approach to existence, which, as far as I know, doesn't work. Although nobody can prove it doesn't work, I guess. But one thing you could try to do. So when you solve the plateau problem or any variational problem, typically, if you want to use sort of direct methods to do it, then you have to take your family of functions and you have to complete it. Right? You have to be able to work in some Sobolev space where you have weak compactness results, and you can actually produce minimize it. And so, in our case, what are we trying to do? Well, we're really trying to construct a metric, which in our case, it's really it's really a measure on the boundary. So the condition on the boundary length is that its boundary length is 1. And so we can think of the boundary arc length as being a probability measure on the boundary. And so when we try to the metric in the interior is determined by the boundary metric together with the conformal class. Okay, and so if we want to take limits of the boundary measures, say fixing the conformal class inside, it's really a matter of maximizing a function of the boundary measure. Okay, and so as we know, boundary measures do have a natural topology in which they're compact. It's the weak star topology, the weak topology on measures. And so, in fact, if we take any measure on the boundary, so let's think of fixing a background metric G naught in the interior, so that determines the Dirichlet integral particles. And if we take a boundary measure mu, we can define a replacement for sigma 1. Right? So we could look at sigma 1 and G naught mu. So we just take the input of this ratio. Now, in order for this to make sense, mu has to be continuous because mu may be a singular measure. We can look at this, we can look at this in FEMA. mu is an H1 intersects C0. So notice that actually H1 of M, the restriction to the boundary is in H1 half, which is pretty close to being continuous. So it's sort of a borderline continuity range. And so if we assume H1 intersects C0, we normalize the integral to 0, then we can define something that we could call sigma 1. So if mu were a smooth measure, that is the density times the arc length measure, S naught, then this would be the ordinary sigma 1. So we can complete our space of boundary measures. We consider arbitrary measures. We can define something that we can call sigma 1. Now I should caution that you don't necessarily have eigenfunctions with this problem. If mu is a singular measure, I don't think you can construct eigenfunctions. You don't have the sort of necessary compactness theorems for arbitrary measures. If mu is too singular, then you can't necessarily achieve it. Okay, but nonetheless, it has some nice properties. In particular, it's upper semi-continuous with respect to weak star conversion. So we're trying to maximize, right? So the idea would be we take a maximizing sequence, we take a limit, and then we argue the limit is actually the maximum, achieves the maximum. So in order to do that, we have to argue upper semi-continuity. And in fact, if you just sort of unwind the definition of this thing, the fact that it's in FEMA, it's very easy to show that it's upper semi-continuous. So you can show if you fix a u, then the integral u squareds converge, and because of the way we're taking the FEMA, it's actually upper semi-continuous. So in particular, you can maximize it. So we could in fact define a number, let's call it sigma double square. And so that's the suit where we allow singular measures on the boundary. Okay, and we can solve the problem. We can construct a maximizer for that just by direct methods. And then the question is it regular? Is that measure regular? And the answer is, I have no idea, actually. There's no regularity argument that I know of to prove that that's regular. There's a paper on this approach by Koparev where he, under various assumptions, he's able to show it's regular, but he's not able to actually show it's regular. That's just to do it unconditionally. Okay, so in other words, it could conceivably happen that by choosing a singular measure on the boundary, you can actually do better than by choosing a smooth measure. There's nothing to preclude that a priori. Okay, so that's an argument that doesn't work. So what argument does work? Well, actually, yeah. So the idea, so it's a problem where you can't just sort of consider all these singular configurations. So the idea is to regularize the problem. So what we do is we construct a special maximizing sequence where the sequence itself maximizes an approximate problem. So there are various situations where this one that comes to mind offhand is like the Sachs-Uhlenbeck approach to studying harmonic maps of S2. Right? So the energy for S2 doesn't satisfy the right compactness properties. You can't get take the limits. On the other hand, it's sort of borderline. If you take the alpha energy, you increase the power a little bit, then you actually get good compaction results. And so the approach in some senses is like that, although the regularization is totally different. But and so what we're going to do is approximate our metrics. We're going to construct our limit as a limit of solutions of a regularized problem. Okay, and so there's a question then, how do you regularize the problem? And well, you want a regularization which is geometric, which is canonical. So actually, that's one of the things about Nataraj-Ville's paper. He also did a regularization, but he took a regularization where he just assumed he was in a particular conformal class, and then he said, well, let's write the metric as a function times that one, and then let's just cut off the function. So the problem with that regularization is it's really sort of coordinate dependent. It depends on that metric. And so I think it's highly desirable to take a geometric regularization. And so there is a natural way to do that, and that's using the heat kernel. So we use the heat kernel to regularize. And so the way we do that is we consider, actually, so we're looking at measures on the boundary, so we consider regularizing by solving the heat equation on the boundary for a time epsilon. So we can take any measure on the boundary and we can take it as initial conditions for the heat equation, and then we can look at the time epsilon solution. And then, of course, that'll be a smooth function for time epsilon, be a smooth measure. So the idea is to consider the heat kernel, and we consider this regularization. So we take any measure on the boundary, and we integrate the k epsilon of x, y, and y, and then the measures lambda epsilon times ds naught. So the heat kernel, of course, depends on the boundary, a background boundary measure, which we have. Maybe that's ds naught. And so we take the lambda epsilon ds naught. That will converge in weak star topology to mu. So we take any measure mu and we can sort of smear it out, and then we can take the limit as epsilon goes to 0. Okay, and then we can study the regularized problem. So we can look at, for a fixed epsilon, we can try to solve the maximizing problem. So we look at Webb epsilon star, which is the soup of these guys, where we maximize over mu and g naught. So g naught is just a background metric inside. We can think of it as being fixed if we want. And we try to maximize that over mu. Now the advantage of the regularization is that the mu epsilons are all uniformly smooth. The derivatives are bounded independently of mu, because mu is a probability measure. So I'm flowing for time epsilon. So all the derivatives of mu epsilons are bounded. So when I take a weak star conversion sequence of mu's, I get actually CK conversion measures of mu epsilon. Okay, so in particular, I have nice compactness results, and I can maximize it quite easily. So mu epsilon will be a smooth probability measure, which maximizes the problem. Okay, so we can solve that problem, and then we can try to let epsilon go to 0. So it turns out the maximizers for this approximate problem have some useful structure, and that's the reason that this argument can work. And so basically the idea is to look at the maximizers of these. And actually, let me just say, maybe I just say a few words here. What we expect to happen, and we don't know for sure what these maximizing measures look like, but we're pretty sure that if you take a positive epsilon, the maximizing measure, mu, for the approximate problem actually has finite support. In other words, it's actually a sum of double measures. And as you let epsilon go to 0, those will converge to a smooth measure. That's part of the theorem. And so the reason we think that is sort of Murphy's law reason. Because if the measure has infinite support, the proof is much easier. So generally in mathematics, if there's something that, if it were true, it would give you a very easy proof, it's usually not true, right? And so from that basic principle, I expect, in fact, it would be interesting to actually try to understand what the, use a computer or something to figure out what the extremal measure looks like. But what we expect is that it's a finite measure, and that the weak star limit is well, we proved the weak star limit is smooth, but it's actually a limit of measures with finite sums of your axis.